Hello everyone. So in this pre-lecture tutorial we're going to discuss how salt solutions can sometimes exhibit acidic or basic behavior. And the reason for that is because when salts break down to give us ions, sometimes those ions are conjugate acids or conjugate bases of weak acids or weak bases, and these species actually still do have acidic and basic behavior. And so we're going to go through how to assess if the salt solution will or will not actually produce a solution that's acidic, if a solution of salt will give us a solution that is basic, or if the solution will remain neutral. And so really, I think probably the most straightforward way to do that is to actually walk you through that thought process with some examples. And so here on the screen we have the following salt solutions that we're actually going to discuss today. The first one is iron 3 chloride. Okay, and when we have iron 3 chloride, if that dissolves fully as a soluble salt, then we should get the following ions. Now, the chloride ion would actually be the anion that we get from hydrochloric acid. And if you recall, there is an inverse relationship between the strength of an acid or base and the strength of its conjugate base. So the stronger an acid is, the weaker its conjugate base, and vice versa. And so since hydrochloric acid is a strong acid, then basically its anion, chloride ion, would actually be a very weak base. So weak, in fact, that we consider it to be a negligible base. So it should not impact pH significantly. However, if we take a look at the iron 3 plus cation, basically, if we were to think of our strong acids, our strong bases, then basically we know that bases that are strong are those hydroxide salts that come from group 1 or group 2 from calcium, strontium, barium. These ions, or these metals, when they're in their ionic forms, would actually be considered to be, and also the group 1 metals, would be considered to be negligible acids, because basically they are the counterions to strong bases. But if you notice, iron is not one of these metals. And so as a result, because of that, then this would actually be considered a weak acid. And so as a result, since the anionic portion of the salt is a negligible base, but the cationic portion is a weak acid, we should expect iron 3 chloride to give us a solution that is acidic. Okay? Let's break apart the following salts. So we have ammonium chloride. Okay, so again, if we consider what ions we get if that salt dissociates fully, we have ammonium cation, and we have chloride anion. And so, taking each of these ions in turn, NH4 plus, or the ammonium ion, is the conjugate acid of ammonia, which is a weak base. And so, as a result, since ammonia is a weak base, then the ammonium ion would actually be a weak acid of some significance. We couldn't consider it to be a negligible acid because those would only come from strong bases, and ammonia is not a strong base, it's a weak base. And so its conjugate acid would still have some acidic character, albeit a weak acidic character. But if we consider the chloride ion, that's the anion from chlorous acid. And chlorous acid is actually a weak acid. And so that means that the chloride ion itself would be a weak base with significant basic behavior. And so in this case, we have competing acid-base behavior. How will we figure out which is going to win, if you will, and what sort of solution I'm going to get when I actually dissolve these salts, or this particular salt, ammonium chloride, in solution? And so the way that we do that is we're going to have to compare the Ka for ammonium ion and the Kb for the chloride ion. So I've included a table here that we can consult. Now if you notice, the ammonium ion has a Ka of 5.6 times 10 to the negative 10. Now here's chlorous acid. We're given its Ka, but I want the Kb of the chloride ion. So what I'm going to have to do is I'm going to have to convert this Ka in the table to Kb by using the relationship that Ka times Kb is Kw for a conjugate acid-base pair. So if I go ahead and run that calculation, that's 1 times 10 to the negative 14th, again assuming we're at 25 degrees Celsius, and I'm going to divide that by 1.2 times 10 to the negative 2. If I go ahead and do that math, I get 8.3 times 10 to the negative 13th. And so if I notice, Ka is actually greater than Kb. And so if Ka is greater than Kb, then that means that the acidic nature will win out, and an aqueous solution of ammonium chloride should be acidic. All right, let's take a look at the final two examples that I have here. I have potassium carbonate. Okay, so again, that would give me potassium cation and 2 moles of the carbonate ion. Now, potassium ion does come from a strong base. From potassium hydroxide. And so as a result, basically this should be a negligible acid, since it's the conjugate acid, if you will, or the cation that comes from a strong base. But carbonate ion comes from a weak acid. And since it comes from a weak acid, then that means that the carbonate ion itself should be a weak base of some significance. So that means that a solution of potassium carbonate should be basic in nature. Okay, now if we're taking a look at calcium bromide, I'll go ahead and write it down here, which is the final example I have on this slide, then if that dissociates, I'll get calcium 2 plus and bromide ion. Now, again, if I think of the base from which this cation would come from, calcium hydroxide is actually a strong base. And so that means that the calcium cation would be a negligible acid. If I consider the bromide ion, basically that had to have come from hydrobromic acid. And so as a result, hydrobromic acid being a strong acid, that means that the bromide ion is also a negligible species in terms of acid-base behavior. It's a negligible base. And so since neither cation or anion significantly impact the pH, then we would expect the calcium bromide solution to be essentially neutral. Okay. Now, as it turns out, we can do calculations of the pH of salt solutions. All right, take, for example, this problem here. I'm being asked to calculate the pH of 0.726 molar anilinium hydrochloride. And they give us the formula. And the solution's in water, and I'm given a Kb value. Okay, so if I have anilinium chloride, then if this is a salt that is soluble, then I should expect the following ions. Okay, the chloride comes from hydrochloric acid, which is a strong acid, but that would mean that the chloride ion would be a negligible base. However, the aniline ion, okay, would come from aniline. And again, considering that I only have a very small selection of strong bases to choose from, if you will, I should know that aniline would actually be a weak base. And so that means that its conjugate acid, the aniline ion, should be a weak acid. So if I were to write out an equilibrium equation showing aniline ions' acidic behavior, then acids are proton donors. And so that means that I would get aniline back again and H3O plus. Okay, so I would have to construct an ice table. Okay, and my initial concentration of the aniline ion based on the dissociation stoichiometry should be 0.726 molar. And I wouldn't initially have any of the ions on the product side, but what's going to happen is the reaction should change in such a way to get these ionic species in solution, at least to some degree, since we're expecting weak acidic behavior. And so that would give me the following expressions for the equilibrium concentration. Now, what I would do is construct the equilibrium constant expression for a weak acid, or the acid dissociation constant, and I would get the following by the law of mass action. Substituting in my equilibrium constant, my equilibrium concentration expressions, I should get this. But I'm going to need a Ka value to set this equal to. And I'm given a Kb. But once again, Ka times Kb should equal Kw. So if I want Ka, I should just take Kw and divide by the Kb value that I was given. So it's 1.0 times 10 to the negative 14th divided by 3.83 times 10 to the negative 4th. And that's going to give me a Ka value of 2.61 times 10 to the negative 11. And I would set my algebraic expression that I got from my ice table equal to that value. Okay? Now again, we're going to assume a small x based on the very small value of this Ka, and that should be x squared over 0.726 is equal to 2.61 times 10 to the negative 11. So if I go ahead and do the algebra, I get x squared is equal to 1.90 times 10 to the negative 11. If I take the square root of both sides, I get an x value of 4.35 times 10 to the negative 6th molar. Now, I'll leave it to you to check, but we should check that the percent ionization is still less than 5%. I think you can tell just visually that that's the case here, because again, we have such a small concentration compared to the initial concentration of 0.726. But then this would actually reflect my hydronium ion concentration, or my hydrogen ion concentration. So if I want the pH from this, all I have to do is take the negative log of my hydrogen ion concentration, which would be the negative log of 4.35 times 10 to the negative 6th. Right, if I go ahead and do that math, then I get a pH of 5.36. All right, so go ahead and try the follow-up assignment. All right, there are similar problems that you will have a chance to practice. All right, and we will discuss this in class. Obviously, if there are any questions, by all means, email, and I'll see you guys in class when next we meet. Have a good night.